Hello, and welcome to our machine learning project of analyzing the home loan redefaulting risk of individuals. This project was completed by me, Mark, Ritesh, and Yash. So let's look at our problem description. Banks and financial institutions are able to basically give out loans to consumers who might be seeking to pay off, for example, their house in this case. So the goal of this transaction basically is for banks to give out the loans and make some money back on interest. And for the lendee, the goal is to basically take the money right now and pay off, for example, their house. The risk in this transaction is that if the lendee isn't able to pay back the loan, meaning if they default, then the lender obviously loses out on the money that they gave, and the lendee loses out on basically they could get sued with the worst. And how do we determine? This is $1 million question. Before giving a lendee a loan, whether they are at a high risk of defaulting, because if they are, then we don't want to give away the loan. So let's look at our data set. We found our data set on Kaggle, and it has a lot of data. For example, just the application train.csv file, it has over 300,000 individual people as data training points, and it has over 100 features. And then there's a lot more CSV files, like the bureau file that we merged with the training file in order to have more detailed data. And we were able to merge them because they share a primary key. All files share a primary key called skid cur, which basically aligns with each individual person. So let's look at our data set and the target values. As we can see in our data, about approximately 10% of people default, and the rest, which is 90%, didn't default. So basically what this means, and it's kind of a problem, is that if our model blindly always predicts that 90% of people don't default and 90% of the time they do default, then technically we would have a very high accuracy, right? But obviously we don't want to do this. That's a terrible model. It doesn't actually take in any features into account. So we will see how we circumvent this problem later on. So let's start with how we pre-processed our data. We started off by just manually dropping useless columns or columns that, for example, had 50% of their data missing because they obviously wouldn't be as helpful. Then we ran a decision tree, which is supervised for learning, to gather the feature importances of all the features that we're currently considering. And then we dropped the features that had low importance, obviously. Then we had to deal with categorical data. There's two ways to deal with it. First, we tried category codes, which means that if a category could have two values such as accepted and rejected, then accepted could have the code 1 and rejected could have the code 2, for example. Basically just one-to-one mapping to numbers. Or we could do one hot encoding, which is what we decided to stick with, and that just means that if a category has the accepted and rejected possible values, then that turns into two new features, which are just the accepted and the rejected. That would just be ones and zeros depending on what the actual value is. And then obviously we imputed our missing values with just 0. So let's look at the decision tree. This is what our decision tree looked like, and this was a shrunken version of it even. So we dropped off some useless features that were towards the end of the decision tree, which means they had very low feature importance in deciding and predicting whether a person defaults or not correctly. And the features with high importance, obviously, we kept. And we will see how the importances kind of look like in data. So for example, laborers, right? If someone has the occupation of either being a laborer or a sales staff, they obviously have a higher chance of defaulting than not defaulting. And if a person is, for example, a manager or a high skilled staff or an accountant, for example, then they have a higher chance of not defaulting rather than defaulting, which means the occupation genuinely makes a difference in predicting correctly whether a person defaults or not. That's why the occupation type ended up closer to here, which is on the higher spectrum of feature importances. And the same is true with the organization type. All right. So before we reduce our dimensions even, we used a standard scalar, which is function provided by scikit-learn, to basically normalize our data before we actually reduced the dimensions of it. Then we realized we had around 250 features, and a lot of those were originated because of one hot encoding. And obviously this is too many features to simply just feed into a learning model and make predictions off of it, right? So what we did was we ran PCA, which is unsupervised learning, and we told PCA to basically shrink to as many components while also keeping 99% of the variance of the data, which is usually a good standard to reduce by. So once we did that, we ended up with 192 components left. And then that's what our data looked like going forward as we feed that data into our actual learning models and classifiers. So our first learning model was a logistic regression. We tuned hyperparameters for it, and that was just the regularization parameter C, which we usually see as lambda. And this turned out to be our best performing model, actually, with validation metrics looking as follows. We used balance accuracy instead of just accuracy, because remember how a lot more people in our data don't default rather than they do default. So what balanced accuracy basically does is that it gives equal weighting to predicting default and not default, instead of the current weighting, which is approximately a 90% to a 10% split. And that's also a similar reason why we use the F1 score. And in all of these, higher number is better. And our precision score is quite high, which is very good. Next, we did a support vector machine classifier. And instead of using quadratic programming, we used stochastic gradient descent as we learned in class. And we did this simply to reduce our model learning times, and also because it gave similar results. And this was the library call we made. We also tuned the hyperparameter of C, which is also regularization constant, same as before, it's just lambda. And our validation metrics were quite similar to the last one, logistic regression, maybe albeit slightly worse. And this is what our confusion matrix looked like here. It was very good at predicting true negatives. And then we next finally did our random forest. We basically tuned these two hyperparameters, which were max depth and the number of estimators. Again, we got very similar validation metrics as we did before, and this one also turned out to be quite good at predicting true negatives. And then a funny joke we came up with while working on this was, what if we hypertune our test train split? Which is basically just the epitome of overfitting, and it's a terrible idea, but we just thought it was funny. And these were some of the noteworthy libraries that we used. And yeah, that's about it. Thank you for watching our machine learning project.